Welcome to Dreaming Through Knowledge. Tonight, we embark on a journey to the very edge of understanding. We travel into the deepest, quietest corners of the cosmos to witness the birth of the most mysterious objects in existence. We are going to explore the creation of black holes, monsters of gravity, gateways to nowhere, engines of time. But to understand the dark, we must first understand the light. To understand the end of everything, we must witness the beginning. If you enjoy these journeys into the deep universe, remember to follow Dreaming Through Knowledge. Your support helps us chart the unknown, one story at a time. Tonight, let your mind drift away from the earth. Leave the city lights, the noise, and the gravity that holds you to your bed. Imagine floating upward, past the moon, past the planets, out into the velvet silence of interstellar space. Here, between the stars, it is cold, it is dark, but it is not empty. We find ourselves in a vast, floating landscape of dust and gas. This is a nebula, a stellar nursery. It is a cloud so immense that it takes light years to cross it, a structure that dwarfs our entire solar system millions of times over. Imagine mountains of smoke, towering pillars of hydrogen and helium glowing faintly in the starlight of distant suns. They are beautiful, silent, and still. These clouds are the raw material of the universe. They are the clay from which stars are sculpted. For millions of years, this gas drifts aimlessly. It is a peaceful, slumbering giant. The atoms here are spread so thin that a cup of this space would contain fewer atoms than the purest vacuum created in a laboratory on Earth. It is a ghost of a cloud, barely there, yet massive in its totality. The temperature here is just a few degrees above absolute zero. It is a stillness so profound that it feels eternal. The atoms of hydrogen float in the void, untouched, moving with a lazy drift. There is no sound, for the medium is too thin to carry it. There is only the slow, cosmic breathing of the galaxy spinning round us. It is a place of waiting. But there is a force here, hidden in the dark, a force that is patient, relentless, and infinite. Gravity. Gravity is the sculptor of the cosmos. It is the invisible hand that shapes the dust. It pulls every atom toward every other atom. It is the desire of matter to be together. Usually, the gas in the nebula is too warm, and the atoms are moving too fast for gravity to take hold. They bounce off one another, resisting the pull. The cloud remains stable, balanced between the outward pressure of heat and the inward pull of gravity. But then, something disturbs the sleep. Perhaps a nearby star explodes, sending a shock wave rippling through the dark like a tsunami across a calm ocean. Or perhaps the cloud drifts through one of the spiral arms of the galaxy, compressing it like a traffic jam. Whatever the cause, the delicate balance is broken. A ripple passes through the smoke. The atoms are pushed closer together. Deep inside the cloud, a pocket of gas becomes slightly denser than its surroundings. It is a seed, a knot in the wood. Suddenly, gravity has a foothold. The denser region pulls on the surrounding gas with a little more strength. It whispers to the atoms nearby, drawing them in. More atoms rush in. The knot grows heavier. Its pull grows stronger. This is the beginning of the collapse. It starts slowly, an imperceptible drift of dust toward the center. If you were watching, you would see nothing change for centuries. But over thousands of years, the movement accelerates. The drift becomes a flow. The flow becomes a rush. The cloud begins to fall inward on itself. It is a landslide of gas, falling toward a center that does not yet exist. As the gas falls, it begins to spin. This is the conservation of angular momentum, the same law that makes an ice skater spin faster when they pull their arms in. Just as water spirals down a drain, the cloud rotates. It flattens into a great, swirling disk, wider than a solar system. The chaos of the cloud organizes into the order of the spiral, and as it falls, it heats up. The friction of atoms colliding, rubbing against one another in the crushing dark, generates heat. The gravitational energy of the fall is converted into thermal energy. The center of the disk begins to glow, a dull, angry red ember in the heart of the cold nebula. It pulses with infrared light, invisible to the eye but warm to the touch of the universe. This is a protostar. It is not yet a star. It is a gathering storm of matter, hungry and growing. It is an infant, feeding on its mother cloud. Gravity continues its work. It squeezes the core tighter and tighter. The temperature rises. 1,000 degrees, 1,000,000 degrees, 10 million degrees. The atoms are stripped of their electrons, turning into a soup of plasma. The pressure at the center becomes unimaginable. The atoms are packed so closely that they can no longer remain separate. They are pushed against their will, overcoming the natural repulsion that keeps them apart. They are crowded into a space where the laws of quantum mechanics begin to take over. The core is trembling on the edge of transformation. And then, in a single transformative moment, the magic happens. The hydrogen atoms, pressed by the weight of the world, slam together and fuse. They forge helium, and in that fusion, a tiny fraction of their mass is lost, converted directly into pure energy according to Einstein's famous equation. A tiny spark is released. One spark becomes two. Two become trillions. Ignition. A shockwave of light blasts outward from the core. It pushes against the crushing weight of the gas. It tears through the surrounding dust veil, illuminating the nebula from within. The star turns on. A new sun is born. The darkness is pushed back. This moment, the birth of a star, is the first step on the long road to a black hole. Because a black hole is not a thing that appears from nothing. It is the ghost of a star. It is the tombstone of a giant. But not just any star. To make a black hole, you need a monster. You need a king. Most stars, like our own sun, are modest. They burn yellow and warm. They live for billions of years, conserving their fuel, shining steadily upon their planets. When they die quietly, shedding their layers like autumn leaves and fading into white dwarfs. They do not have the mass to tear a hole in reality. But in the richest parts of the nebula, where the gas is thickest and the gravity is strongest, monsters are born. These are the massive stars, the O-type and B-type stars, blue supergiants. They are 10, 20, 50 times heavier than our sun. They are the titans of the galaxy. They are terrifyingly bright. They burn not with a gentle yellow glow, but with a fierce, blinding blue-white incandescence. They are thousands of times more luminous than the sun. They pour out ultraviolet radiation that ionizes the gas around them, making the nebula glow like a neon sign. They are the rock stars of the universe. They live fast and they die young. Let us look closely at one of these giants. Imagine hovering near it, shielded from its lethal heat. It is immense. If you placed it in the center of our solar system, its surface would extend out past the orbit of Mars, swallowing the Earth whole. We would be deep inside its belly. Its gravity is immense, crushing the core, with the weight of 1,000,000 Earths. The pressure at the center is 1,000,000,000 times greater than the pressure at the bottom of our deepest ocean. It is a pressure that tries to crush matter out of existence. To resist this crushing weight, to stop itself from collapsing instantly, the star must burn furiously. It consumes its hydrogen fuel at a staggering rate, converting millions of tons of matter into energy every single second. It is a desperate, frantic burning. It is a constant war, a stalemate between two titans. Inward pulls gravity, trying to collapse the star into a point. Outward pushes the energy of fusion, the pressure of light itself, holding the star up. This delicate balance is called hydrostatic equilibrium. It is a stalemate that lasts for millions of years. The star hangs in the sky, a perfect sphere of plasma, held in place by its own burning heart. It looks peaceful from a distance, but inside it is a nuclear inferno. The photons of light created in the core struggle for thousands of years just to reach the surface, bouncing off the dense plasma before finally flying free into the universe. But this war cannot last forever. Gravity is patient. Gravity never tires. It does not need fuel. It simply is. The star, however, has a limit. It has a finite amount of fuel. It is living on borrowed time. Deep in the core, the hydrogen begins to run out. The ash of the fusion reaction, helium, builds up in the center. The fire dims. The outward pressure weakens. Gravity senses the weakness immediately. It pushes inward. The core begins to shrink. But this shrinking has a side effect. As the core is squeezed tighter, the temperature spikes again. It gets hot enough to fuse the helium ash. The star finds a second wind. It begins to burn helium, fusing it into carbon and oxygen. This new burning is even hotter than the first. The intense heat causes the outer layers of the star to expand wildly. The star swells. It grows larger and larger, consuming the space around it. Its surface cools as it expands, turning from a blinding blue to a deep, angry red. It becomes a red supergiant. Now, it is a behemoth. It is the size of the orbit of Jupiter. It is a tenuous, glowing ghost, creating a stellar wind that blows millions of tons of gas into space. Inside, deep in the tiny, dense core, the alchemy continues. The star is creating the elements of life. In its dying throes, it forges carbon, the basis of biology. It forges neon, the light of our cities. It forges magnesium and oxygen. It builds the periodic table in its belly, layer by layer, like an onion. Each layer burns a different fuel, hotter and faster than the last. First, hydrogen lasts for millions of years. Then helium lasts for a few 100,000. Then carbon lasts for a few thousand. Neon burns in a few years. Oxygen burns in a few months. Silicon burns in a few days. The star is racing toward a cliff. Finally, the star tries to fuse silicon. It pushes the atoms together with the last of its strength to create iron. And here, the story takes a fatal turn. Iron is the poison pill. Iron is the ash of the stellar furnace. Up until now, fusing atoms released energy. It created the outward push that held the star up. But iron is different. Iron has the most stable nucleus in the universe. To fuse iron does not release energy. It consumes energy. It steals heat. The moment iron is formed in the core, the star makes a fatal mistake. It tries to burn it, but instead of getting a burst of energy, the core suddenly cools. The energy drain is catastrophic. The outward pressure that has supported the star for millions of years vanishes in an instant. The engine stops. The light goes out. The war is over. Gravity has won. The stalemate is broken. The core, an iron sphere the size of the Earth, incredibly dense and hot, looks up at the millions of trillions of tons of star hanging above it and realizes it has nothing left to hold them back. The silence in the core is profound. The fusion roar ceases. For a fraction of a second, the star hangs there, suspended by its own inertia, unaware that it is already dead. The outer layers are still shining, still floating, but the foundation has been removed. Then the collapse begins. It does not fall like a stone. It falls like light. In a fraction of a second, faster than you can blink, faster than a nerve impulse travels from your finger to your brain. The core collapses. An object the size of the Earth collapses into a ball the size of a city. The electrons are crushed into the protons, turning them into neutrons. The density skyrockets to numbers that have no names. The speed of the infall reaches 70,000 kilometers per second, 25% the speed of light. This collapse is the trigger for the most violent event in the universe since the Big Bang. But before the explosion, there is the implosion. The outer layers of the star, the vast envelope of hydrogen and helium that extended for millions of kilometers, suddenly find themselves in freefall. They rush inward, chasing the core, falling at supersonic speeds. They are crashing down onto the center of the star with the weight of a galaxy. The density becomes infinite. The temperature becomes infinite. The fabric of space begins to tear under the stress. We are standing on the precipice of the event. The star is trembling. The core has collapsed. The fuse is lit. The vast machinery of the star is about to tear itself apart in a cataclysm of light and power. But for this specific star, something unusual is about to happen. The core is too heavy. The neutrons cannot hold the weight. To understand what comes next, to understand how this fiery death leads to the birth of darkness, we must look at the physics of the explosion itself. We must see how matter is squeezed so tightly that it punches a hole in the fabric of space-time. We must witness the transition from the loudest noise in the universe to the deepest silence. In the next chapter, we will witness the supernova. We will watch the giant star detonate, illuminating the galaxy and leaving behind a seed of pure gravity. We will see how the light dies and how the shadow is born. We will stand at the moment where physics ends and the unknown begins. For now, imagine that blue giant one last time, hanging in the silence of the nebula. A king on his throne, surrounded by his court of gas and dust, unaware that his reign is ending. Burning bright, burning fast, destined for a darkness deeper than night. Drift in the glow of that ancient light before the shadows fall. The collapse of the core is absolute. It is a catastrophe of physics. In less than a second, a time frame too short for the human mind to process, an iron sphere the size of the Earth is crushed into a ball of neutrons, no wider than a city. The speed of this implosion reaches 70,000 kilometers per second. It is a free fall of matter into the center of existence, a landslide of atomic proportions. The outer layers of the star, the vast, glowing envelope of hydrogen and helium that extended for millions of kilometers into space suddenly find themselves with nothing to stand on. The foundation has vanished. They rush inward, chasing the core, falling at supersonic speeds. They are like a ceiling collapsing when the pillars are removed, crashing down with the weight of 1 billion worlds. But the core can only shrink so far. Nature has a final line of defense. When the neutrons are packed so tightly that they are touching, shoulder to shoulder in a subatomic crowd, a new force emerges, the strong nuclear force. It acts like an impenetrable wall. It is the force that binds the universe together, and now it becomes a shield. The collapsing core hits this wall and stops dead. This sudden stop is the most violent braking maneuver in the universe. The core, having collapsed at 1/4 of the speed of light, becomes rigid in an instant. It effectively becomes a solid surface, harder than diamond, hotter than 1 billion suns. The energy of that motion has to go somewhere. It cannot be destroyed. So it turns around. It turns into a shock wave. It bounces back. The infalling outer layers of the star crash onto the rigid core and rebound with titanic force. Imagine an ocean crashing against a cliff, but the ocean is made of plasma, and the cliff is made of neutrons. A wave of kinetic energy blasts outward. It tears through the infalling gas, reversing its direction, turning the implosion into an explosion. This is the supernova. It is the death scream of the star. From the outside, for a few hours, nothing seems to have changed. The surface of the blue giant star remains calm, floating in the silence of the nebula, unaware that its heart has just stopped beating. The shock wave is still traveling through the deep interior, fighting its way to the surface, chewing through millions of miles of dense gas. But there is a signal that travels faster than the shock wave. Neutrinos. These are ghostly subatomic particles, produced in the trillions by the crushing of the core. They interact with almost nothing. They fly straight through the dense matter of the star as if it were glass. They fly through the nebulas, through planets, through us. They flood out into the galaxy, the first messengers of the death. If you were standing near the star, the flood of invisible neutrinos would be so intense it would be lethal. But to the universe, they are a silent whisper before the scream. They carry away 99% of the energy of the collapse, leaving the shock wave to finish the job. Then the shock wave reaches the surface. It breaks through the photosphere. The star breaks. The surface bulges, cracks, and then vaporizes. A blinding flash of light erupts into the darkness. In a matter of seconds, the star releases more energy than our sun will emit in its entire 10 billion year lifetime. It creates a flashbulb effect that illuminates the dust of the surrounding nebula, painting the dark clouds in hues of violet and shock blue. For a few weeks, this single dying star can outshine the entire galaxy of 100 billion stars combined. It becomes a beacon visible across the universe. If it happened in our own galaxy, it might be visible during the day, a second sun hanging in the blue sky, casting shadows that are too sharp, too bright. But this violence is also an act of creation. Inside the expanding fireball between the shock wave and the cooling gas, a frantic alchemy is taking place. The heat and pressure are so intense that atoms are fused together not in orderly steps, but in chaotic collisions. This is nucleosynthesis on a grand scale. This is where the heavy elements are born. The star, having spent its life making carbon and oxygen, now forces neutrons into nuclei to create the rare treasures of the cosmos: gold, platinum, uranium, the silver in a ring, the mercury in a thermometer, the iodine in your blood. All of them were forged in this single, fleeting moment of destruction. The supernova is the universe's blast furnace. It is the only place hot enough to build the upper half of the periodic table. Every gold atom on Earth was once inside a star that exploded. We are wearing the debris of a cosmic catastrophe. The explosion scatters these new elements deep into space. They mix with the surrounding nebula, enriching it, seeding it with the ingredients for future planets and future life. The death of the giant makes the life of the dwarf possible. We are made of this dust. We are the afterlife of stars. As the light fades over the coming months and the fireball expands into a wispy, colorful nebula, a remnant that will expand for thousands of years, we must look back at the center. The smoke has cleared. The noise has stopped. What remains? If the star was large, but not too large, perhaps 10 to 20 times the mass of the Sun, a neutron star remains. This is a city-sized ball of crushed matter spinning, hundreds of times a second, pulsing with magnetic fields. It is a wondrous object, but it is not our destination. We are interested in the true giants, the stars that began their lives with 30, 40, or 50 times the mass of the Sun. For these titans, the neutron core is not strong enough. The gravity is too great. The wall of the nuclear force crumbles. The shock wave that exploded the outer layers pushed back against the core, adding pressure to the center. And as the outer layers flew away, some of the matter fell back, a fallback of gas that rains down onto the neutron ball, adding weight to the scale. The limit is reached. The Tolman-Oppenheimer-Volkoff limit. The neutrons themselves are crushed. They fracture. There is nothing left in the laws of physics to stop the collapse. No force known to nature, not electron pressure, not neutron pressure, not heat, can push back against the overwhelming weight of the mass. The core begins to shrink again. It resumes the fall that started when the iron was formed. It gets smaller and smaller. It shrinks past the size of a city, past the size of a mountain, past the size of a house. The density climbs toward infinity. The gravity at the surface of this shrinking object becomes so intense that space itself begins to warp. It does not just pull on matter, it pulls on the geometry of the universe. It curves inward, wrapping around the mass like a heavy blanket on a bed. Light rays trying to pass near it are bent, looping around the back of the object. Light rays trying to escape from it are pulled back, climbing uphill against a slope that keeps getting steeper. The light turns red as it fights the gravity, losing energy, gasping for breath. Finally, the object shrinks past a critical mathematical boundary. This is the Schwarzschild radius. It is the point of no return. It is determined solely by the amount of mass crushed into the point. For a mass equivalent to the Earth, this radius would be the size of a marble. For our dying star, it is a sphere about 30 kilometers across. At this precise moment, the escape velocity, the speed you would need to break free from the gravity, exceeds the speed of light. Since the speed of light is the cosmic speed limit, the absolute maximum velocity in the universe, this means that nothing can escape. Not matter, not radio waves, not light. The door slams shut. The region of space cuts itself off from the rest of the universe. The communication line is severed. A black hole is born. From the outside, we see darkness. A perfect, spherical shadow appears in the heart of the explosion remnant. It is a hole in reality. It is not a solid object like a planet. It is a region where space falls inward faster than light can swim outward. It is a waterfall of space. This boundary, this surface of shadow, is called the event horizon. It is the edge of the waterfall. Below it, there is no future that leads away. All paths, all timelines, all destinies lead down. To cross the horizon is to leave the observable universe forever. Inside the horizon, the mass continues to collapse. It does not stop at the surface, because there is no surface. It falls until it occupies zero volume. It becomes a singularity, a point of infinite density and infinite gravity. Here, our understanding of physics breaks down completely. The math yields infinity, which is nature's way of saying, you do not understand this yet. Space and time as we know them cease to exist. Time becomes space, and space becomes time. The singularity is a question mark at the center of the dark. But let us stay outside the horizon for now. Let us float in the safe distance and observe this newborn monster. It is small, tiny, compared to the star that birthed it, yet it holds the mass of 10 suns. It is a heavy nothingness. It is invisible, yet it has a presence. You can feel its gravity tugging at you, a heavy, silent hand. The space around it acts like a lens, bending the light of the stars behind it into strange, circular halos. It creates an Einstein ring, a mirage of gravity that warps the background sky. The black hole wears the galaxy like a distorted cloak. The black hole is quiet now. It has consumed its parent star's core. The rest of the star has been blown away in the supernova, drifting off to become a nebula. The black hole sits alone in the cooling debris, a predator waiting in its den. It is stable. It is waiting. But black holes are rarely solitary. The universe likes pairs. Most massive stars are born in binary systems, two giants dancing around each other, born from the same cloud. Imagine that our black hole has a companion, a blue supergiant that survived the explosion. Perhaps it was far enough away to weather the blast. It is still burning, still shining, but now it is orbiting a ghost. Gravity binds them. The black hole orbits the living star, and the star orbits the black hole. They circle a common center of gravity in a deadly, beautiful waltz. One made of light, the other made of shadow. Over time, the living star expands as it ages, just as its brother did. Its outer layers of gas puff out, becoming loose and tenuous. They wander too close to the gravitational well of the black hole. The gravity of the dark object begins to strip the star. The black hole begins to feed. It strips gas from the surface of its companion. A stream of hot plasma flows from the star to the hole, like water pouring from a pitcher. But the gas does not fall straight in. In space, everything spins. Because the system is rotating, the gas misses the hole slightly. It swings around, caught in orbit. It forms a flat, spinning ring of matter around the event horizon. This is the accretion disk. It is the waiting room for the singularity. This disk is one of the most violent places in the universe. The gas is swirling at a significant fraction of the speed of light. Layers of gas rub against each other, creating friction that heats the matter to millions of degrees. The disk glows. It shines not with visible light, but with high-energy X-rays. The invisible black hole has surrounded itself with a ring of fire. It has become a lighthouse of death. It has painted itself into the sky. We can see these X-ray beacons from Earth across thousands of light years. They are the first way we discovered black holes, not by seeing the darkness, but by seeing the scream of the matter falling into it. We saw the meal, not the eater. As the gas spirals inward, losing energy, it inches closer to the edge. It crosses the innermost stable circular orbit. This is the last safe place to stand. Beyond this line, gravity is too strong for orbit. There is no centrifugal force that can save you. The gas plunges. It fades from view as it crosses the horizon, its light stretched into invisibility by the gravity. It adds its mass to the black hole. The hole grows. With every atom it swallows, the horizon expands slightly. This feeding process can last for millions of years. The black hole consumes its companion slowly, growing from 10 solar masses to 20 to 50. It is an insatiable eater. The companion star is slowly unspooled, turned from a sphere into a disk, and then into nothingness. But sometimes, the feeding is too fast. The black hole cannot swallow the matter as quickly as it arrives. The accretion disk becomes choked with plasma. The magnetic fields, twisted by the spin of the black hole, become like coiled springs. They snap. They launch jets of particles from the poles of the black hole. These jets blast outward at nearly the speed of light, piercing the interstellar medium for thousands of light years. They are cosmic blowtorches, powered by the spin of the singularity. So the black hole is not just a hole. It is an engine. It converts matter into energy with an efficiency that makes nuclear fusion look feeble. It is the ultimate power source of the cosmos. As we watch this spectacle, the glowing disk, the jets, the slow devouring of the companion star, we realize that this is only the beginning of the black hole's life. The story has chapters we can barely conceive. The companion star will eventually die. It, too, might explode and become a black hole or a neutron star. Then, we will have two remnants dancing in the dark, two holes in reality, spiraling toward one another. This sets the stage for an even greater event, a collision that will shake the very fabric of space and time, sending gravitational waves rippling out to the edge of the universe. But there are other black holes, monsters so large they defy imagination. They do not live in the quiet fields of binary stars. They live in the crowded, chaotic downtowns of the galaxies. These are the supermassive black holes. They are millions, even billions of times the mass of the Sun. They are the anchors of the spiral arms. How do they form? Do they start as stars and eat for billions of years? Or are they born from the direct collapse of massive primordial clouds at the dawn of time? In the next chapter, we will travel to the center of the galaxy. We will meet Sagittarius Aes, the sleeping dragon at the heart of the Milky Way. We will see how these giants shape the destiny of entire galaxies, holding them together with their gravity and sculpting them with their jets. We will see that without the dark heart, the galaxy might not exist at all. For now, let your mind rest on the image of the event horizon, a perfect sphere of silence, a boundary where time stops, a shadow that proves the light. Float in the presence of the ultimate mystery and drift into the quiet. We have witnessed the death of a star. We have seen the birth of a stellar mass black hole, a dark jewel, born from the ashes of a giant sun. But now, we must look deeper. We must look beyond the individual stars into the heart of the galaxy itself. We are going to visit a monster. We travel 26,000 light-years from Earth, moving inward along the spiral arms of the Milky Way. We pass through the calm suburbs of the galaxy, where stars like our sun live quiet lives. As we move closer to the center, the neighborhood changes. The stars become crowded. In our part of the galaxy, the nearest star is 4 light-years away. Here, near the core, stars are packed together like commuters on a busy train. If you lived on a planet here, the night sky would be blindingly bright, filled with 1,000,000 suns, casting shadows in every direction. The gas is thicker, the radiation is intense. It is a chaotic, turbulent place, but there's an order to the chaos. Everything, every star, every cloud of dust, every planet is moving around a central point. They are orbiting something invisible. This is the galactic center, and residing here in the constellation of Sagittarius is a radio source known as Sagittarius A. It is not a star, it is a supermassive black hole. If the black hole we met in the last chapter was a city, this one is a solar system. It contains the mass of 4 million suns, 4 million stars crushed into a single point of infinite density. It is the anchor of our galaxy. For decades, astronomers suspected something was there. They saw the radio waves. They saw the infrared light piercing through the dust. But the definitive proof came from watching the stars themselves. For over 20 years, telescopes tracked the movements of stars near the center. They saw them whipping around an empty patch of space at incredible speeds, millions of kilometers per hour. They were dancing with a ghost. The laws of gravity told us that only something incredibly small and incredibly massive could cause such motion. The math was undeniable. But how did it get here? How does nature build a black hole this big? A stellar black hole forms from the collapse of a single star, but there is no star large enough to create Sagittarius A. Even the largest stars are only 100 times the mass of the Sun. This thing is 4 million times heavier. The origin of supermassive black holes is one of the greatest mysteries in modern astrophysics. There are 2 main theories, 2 paths through the dark. The first is the path of gluttony. It suggests that these giants started small, perhaps billions of years ago. When the galaxy was young, a cluster of massive stars formed in the dense core. They lived, died, and exploded, creating a swarm of stellar black holes. Over eons, these black holes merged. They collided and swallowed one another, growing larger with each meal. They fed on the gas and dust that swirled around them. They grew fat on the chaos of the early universe. It is a story of slow, relentless accumulation. But there is a problem with this theory. It takes time to eat. Black holes have a speed limit on feeding, the Eddington limit. If they eat too fast, the radiation from the hot gas pushes the food away. When we look deep into the past, at the very edge of the observable universe, we see quasars, supermassive black holes that existed when the universe was less than 1 billion years old. They are too big, too early. They shouldn't exist yet. This leads to the second theory, direct collapse. This is a story of a different kind of birth. Imagine the universe just after the Big Bang. It is filled with pristine gas, hydrogen, and helium. There are no stars yet. In some places, these clouds of gas are colossal, millions of times the mass of the Sun. Usually, when a cloud collapses, it fragments into many small stars. But perhaps under specific conditions, if the gas is kept hot by radiation from nearby galaxies, it does not fragment. It collapses as a single unit. A cloud weighing 1,000,000 suns falls inward. It bypasses the star phase entirely. It never ignites fusion. It simply crushes itself under its own weight, imploding directly into a massive black hole. A monster born fully formed from the womb of the cosmos. Whichever story is true, the result is the same. Every large galaxy we look at seems to have one of these titans in its heart. The Milky Way, Andromeda, M87. They are the standard equipment of the universe. But Sagittarius A is currently a sleeping giant. It is relatively quiet. It is not feeding voraciously. It snacks on the occasional wisp of gas or a stray asteroid, flaring up briefly in X-rays, but mostly it sits in silence. Other galaxies are not so peaceful. In the early universe, or in galaxies that have recently merged, the central black hole is a beast. It is surrounded by a massive accretion disk of gas, shining brighter than 1,000,000,000,000 stars. These are quasars. A quasar is the most luminous object in the universe. It is a black hole eating a galaxy. The energy released by the infalling matter is so intense that it shoots jets of plasma out of the galaxy's poles at near light speed. These jets can travel for millions of light years, punching holes in the intergalactic medium, time. Threes. These jets are the sculptors of the universe on the largest scales. They heat up the gas around the galaxy, preventing it from cooling down to form new stars. The black hole acts as a thermostat. It controls the growth of the galaxy. If the galaxy makes too many stars, the gas falls into the black hole. The black hole turns on, blasts the gas away with its jets, and star formation stops. It is a feedback loop. The tiny black hole, tiny compared to the galaxy, controls the fate of the entire system. They are linked. The size of the black hole is perfectly correlated with the size of the galaxy's central bulge. It seems you cannot have a galaxy without a black hole, and you cannot have a black hole without a galaxy. They evolve together, a cosmic symbiosis. But what happens if you fall into one of these supermassive giants? It is a very different experience from falling into a stellar black hole. With a small black hole, the gravity changes drastically over short distances. The tidal forces are extreme. If you fell feet first, the pull on your feet would be millions of times stronger than the pull on your head. You would be stretched into a long, thin noodle, a process physicists cheerfully call spaghettification. You would be torn apart before you even reach the horizon. But a supermassive black hole is different. Because it is so huge, its event horizon is far away from the singularity. The gravity is immense, but the change in gravity is gentle. The tidal forces are weak at the horizon. You could cross the event horizon of Sagittarius A without feeling a thing. You would drift across the point of no return, alive and whole. You would look out and still see the stars of the galaxy. You would look in and see darkness, but your fate would be sealed. You have entered a region where space falls inward faster than light. No rocket, no signal, no prayer can escape. You are now part of the black hole. You will drift inward for hours, perhaps days, until you reach the center. And what lies at the center? The singularity. General relativity tells us it is a point of infinite density. But quantum mechanics tells us that points of infinite density are impossible. They violate the rules of the quantum world. This is the greatest conflict in physics, the war between the smooth curves of Einstein and the pixelated jitter of quantum particles. The interior of a black hole is the battleground where these two theories meet. Some theorists suggest that the singularity is not a point, but a gateway, a wormhole, an Einstein-Rosen bridge connecting to another part of the universe, or perhaps another universe entirely. Others suggest a Planck star, a dense knot of quantum foam that bounces back in extremely slow motion, or a fuzzball, a tangle of vibrating strings. We do not know. The event horizon protects the secret. It is a cosmic censorship. Whatever happens inside stays inside. But black holes do not just destroy, they also preserve. There is a concept called the holographic principle. It suggests that all the information about the stuff that falls into a black hole is not lost. Instead, it is encoded on the surface of the event horizon, like a 2D sticker on a 3D ball. If this is true, then the black hole is the ultimate hard drive. It stores the record of everything it has ever eaten. It preserves the history of the galaxy in a sphere of silence. And recently, we have done the impossible. We have looked the monster in the eye. In 2019, the Event Horizon Telescope, a network of radio dishes spanning the entire Earth, captured an image of the supermassive black hole in the galaxy M87, and later, an image of our own Sagittarius A. We saw a ring of glowing fire, the accretion disk, surrounding a central shadow. We saw the silhouette of the void. We proved that Einstein was right, even in the most extreme environment in the universe. It was a donut of light in the darkness, a picture that will hang in the galleries of science forever. But black holes are not eternal. They too can die. It just takes a very, very long time. Stephen Hawking showed us that black holes are not truly black. They glow with a faint radiation, Hawking radiation. They slowly leak energy into space. Over trillions of years, particle by particle, they evaporate. They shrink. As they get smaller, they get hotter and faster. Until, in the distant future of the universe, long after the stars have burned out, the last black holes will explode. But that is an eternity away. For now, they are the rulers of the dark. In the next chapter, we will leave the center of the galaxy and look at the most exotic and theoretical aspects of these objects. We will ask, can we use them? We will explore the concept of the Penrose process, extracting energy from a spinning black hole. We will look at time dilation near the horizon, how a black hole could be a time machine to the future. And we will explore the possibility that our entire universe is living inside a black hole. For now, float in the orbit of Sagittarius A. Watch the stars whip around the invisible point. Feel the power of the anchor that holds our galaxy together. A silent, sleeping giant in the dark. We have journeyed to the center of the galaxy and met the monster that holds it together. We have seen the raw power of gravity to crush matter into oblivion. But black holes are not merely destroyers. They are the most sophisticated objects in the universe. They are machines made of space and time. To understand their true potential, we must look beyond the simple idea of a hole in the ground. we must look at what happens to time itself when it brushes against the infinite. Imagine you are an explorer in a spacecraft, hovering safely outside the event horizon of a supermassive black hole. You decide to send a probe down to investigate. You watch it fall. As the probe approaches the horizon, something strange happens. From your perspective, the probe begins to slow down. It moves sluggishly, as if it is falling through invisible syrup. The light coming from it begins to change color. It shifts from white to yellow, to deep red, and then into the infrared. This is gravitational time dilation. The gravity is pulling so hard on the light waves that it stretches them out, sapping their energy. It is also pulling on time itself. To you, the watcher, the probe never actually crosses the horizon. It slows down until it seems to freeze, plastered against the black sphere like a photograph. Its image fades, becoming dimmer and redder, until it vanishes into silence. To the outside universe, nothing ever truly falls into a black hole. It just fades away at the door. But for the probe, the experience is radically different. It feels no slowing. It sees its own clock ticking normally. It crosses the horizon without a bump, falling freely into the dark. If the probe looked back, however, it would see something extraordinary. Because time outside is moving faster relative to the probe is effectively traveling into the future. If it could look back at the universe it left behind, it would see the stars aging and dying in fast motion. It would see the galaxy rotate like a spinning wheel. A black hole, then, is a one-way time machine. It is a ticket to the end of the universe. But there is more to these objects than just time distortion. Most stars in the universe spin. They rotate on their axes. And when a massive star collapses to form a black hole, that spin does not disappear. In fact, it gets faster. Conservation of angular momentum dictates that as the mass shrinks, the rotation speed must increase. A black hole born from a spinning star spins incredibly fast. Some rotate at nearly the speed of light. This spin changes everything. It transforms the black hole from a simple point into a complex engine. A spinning black hole drags the fabric of space along with it. Imagine a ball spinning in a bowl of thick honey. As the ball turns, the honey turns with it. Space acts like the honey. This phenomenon is called frame dragging. Around a spinning black hole, space itself is twisted into a vortex. If you were to hover near it, you would find it impossible to stand still. Even if you fired your rockets to hold your position, the space you occupy would be moving. You would be dragged around the black hole, riding the carousel of geometry. This region of twisting space is called the ergosphere. It sits just outside the event horizon, shaped like a flattened pumpkin. The ergosphere is a place of fascinating physics. It is the only place in the universe where you can enter a region of extreme gravity and still escape, provided you are fast enough. And it is here that a sufficiently advanced civilization could perform the ultimate magic trick. They could steal energy from the black hole. This idea was proposed by the physicist Roger Penrose. It is known as the Penrose process. Imagine flying a ship into the ergosphere. You are being dragged around at tremendous speed by the twisting space. You carry a heavy weight with you, perhaps a container of waste matter. At the point of maximum speed, you jettison the weight. You throw it into the black hole. If you do the math correctly, you can throw the weight in such a way that it is swallowed by the horizon, but the recoil kicks your ship outward. The kick you receive contains more energy than you had when you entered. You leave the ergosphere faster than you came in. You have gained free energy. Where did this energy come from? It came from the black hole itself. By dropping the weight, you slowed down the black hole's spin slightly. You harvested its rotational energy. A spinning supermassive black hole contains a staggering amount of energy. It holds more usable power in its spin than all the stars in the galaxy emit over their entire lifetimes. It is the ultimate battery. We can imagine in the distant future, when the stars begin to burn out and the galaxy grows dark, civilizations migrating towards these giants. They would build cities in orbit around the black hole, dipping into the ergosphere to harvest the power they need to survive the long, cold night of the universe. They would huddle around the embers of the singularity, warming themselves not with fire, but with gravity. But let us go deeper. Let us pass through the ergosphere and cross the event horizon of this spinning monster. In a non-spinning black hole, the center is a point, a singularity where you are crushed. But in a spinning black hole, the centrifugal force of the rotation fights against the gravity. It opens up the center. The singularity stretches. It becomes a ring singularity. If you could survive the journey, if the tidal forces didn't tear you apart, you might be able to fall through the center of this ring without touching the singularity itself. You would pass through the eye of the needle. Where would you go? The mathematics of general relativity suggests a strange possibility. The ring might act as a gateway, a wormhole. It might lead to another region of our own universe, millions of light years away. Or it might lead to a different universe entirely, a baby universe expanding into its own dimension. This is the concept of the Einstein-Rosen bridge, a tunnel through space-time. Of course, this is highly theoretical. Most physicists believe that the wormhole would be unstable. The moment a single photon of light tried to pass through, the tunnel would collapse, crushing the traveler. Or perhaps the radiation inside would be lethal long before you reach the ring. But the math allows it. And in physics, if the math allows it, nature often finds a way to do it. There's another boundary we must cross before we reach the center. It is called the inner horizon, or the Cauchy horizon. If you fall into a black hole, you are seeing the light from the universe falling in behind you. But as you slow down near the inner horizon, you might see the entire future history of the universe play out in a fast-forward blur. All the light that will ever fall into the black hole for billions of years to come catches up to you at once. You would be bathed in the concentrated light of eternity, a blinding flash containing the end of time. This intense radiation might be the firewall that prevents anyone from passing through the wormhole. It is the guardian of the multiverse. Let us pull back to a safer distance. Let us look at the black hole not as a destination, but as an object in the sky. Surrounding the black hole, at a distance of 1.5 times the Schwarzschild radius, is a place called the photon sphere. Here, gravity is so strong that light particles, photons, are forced into orbit. They circle the black hole like planets around a sun. If you were standing in the photon sphere, the view would be mind-bending. If you looked sideways, you would see the back of your own head. The light reflecting off your helmet would circle the black hole and return to your eyes. you would see infinite copies of yourself and infinite copies of the universe wrapped in rings of light. It is a hall of mirrors created by gravity. This sphere is unstable. You cannot stay there long. A tiny nudge would send you spiraling down into the dark or flinging you out into space. It is a razor's edge of light. These exotic features, the time dilation, the ergosphere, the photon sphere, make black holes the most extreme laboratories in existence. They test the limits of what is possible. But perhaps the most profound idea is not what happens around a black hole, but what a black hole is. Look at the universe around us. We see galaxies, stars, and vast empty spaces. We live in a cosmos that started with a Big Bang, a singularity, and expanded. Some physicists have noticed a striking similarity. The mathematics describing the Big Bang are eerily similar to the mathematics describing the formation of a black hole. Could it be that our universe is the interior of a black hole? Imagine a star collapsing in a parent universe. It forms a singularity. But instead of crushing matter into nothing, the singularity bounces. It expands outward into a new dimension, creating a new bubble of space-time. That bubble is a new universe. To the observer in the parent universe, it looks like a black hole. To the observer inside the bubble, us, it looks like a Big Bang. This is the theory of cosmological natural selection. It suggests that universes reproduce. Universes with physical laws that allow stars to form will create many black holes. Each black hole creates a baby universe. Universes that cannot create stars, universes where gravity is too weak or too strong, will not reproduce. They are evolutionary dead ends. So, we live in a universe perfect for life, not by accident, but because our universe is the successful offspring of a long line of black hole-making universes. We are living inside the event horizon of a higher reality. It is a dizzying thought. It connects the smallest particles to the largest structures. It implies that every black hole in our night sky is a seed, a pregnant possibility, holding a vast new reality within its dark heart. But even black holes, these engines of eternity, are not truly immortal. They have a lifespan. They have a destiny. Time, threes. In the 1970s, Stephen Hawking made a discovery that shocked the scientific world. He applied quantum mechanics to the edge of the black hole and found that the horizon is not perfect. It leaks. Quantum fluctuations near the horizon create pairs of particles. One falls in, the other escapes. The one that escapes carries energy away. This is Hawking radiation. It means that black holes glow. They have a temperature, and because they are losing energy, they are shrinking. It is an incredibly slow process. For a black hole the size of the Sun, it would take longer than the current age of the universe to lose even a fraction of its mass. But time is long. In the far, far future, long after the last star has died, the universe will be dominated by black holes, and then they too will begin to fade. In the next chapter, we will travel to that distant future. We will witness the era of black holes. We will see the slow evaporation of the giants. And we will witness the final moments of a black hole's life, a moment not of silence, but of explosive power. We will see what happens when the paradox resolves itself. For now, float in the distorted light of the photon sphere. Look into the mirror of gravity. See the universe reflected back at you, twisted and beautiful. Rest in the knowledge that even in the deepest trap, there is a way through. We have traversed the edge of time and peered into the possibility of other universes. We have seen the black hole as an engine and a gateway. But now, we must return to the realm of the visible. We must ask a simple, yet impossible question. What does it look like to stand face to face with a ghost? For decades, black holes were nothing more than equations. They were mathematical scribbles on a chalkboard, ghosts in the machine of general relativity. Physicists knew they should exist, but they existed only in the abstract. They were invisible by definition. How do you take a picture of a shadow on a dark night? To answer this, we must travel to a very specific region around the singularity. We must pull back from the event horizon, back through the ergosphere, to a distance of exactly 1.5 times the Schwarzschild radius. Here, we find the photon sphere. This is one of the most visually haunting places in the cosmos. Gravity here is so precise, so overwhelmingly strong, that it grabs particles of light, photons, and forces them into a perfect orbit. Light does not escape, nor does it fall in. It circles. Imagine floating in this region. You would not need a mirror to see yourself. If you looked straight ahead, you would see the back of your own head. The light reflecting off your helmet would travel around the black hole, circle the abyss, and return to your eyes. You would see yourself from behind, suspended against the backdrop of the stars. But it would not just be one image. Because light can orbit multiple times before escaping or falling in, you would see infinite versions of yourself. You would see a ring of your own heads, getting smaller and smaller, stretching off into infinity. You would be standing in a cosmic hall of mirrors, created not by glass, but by gravity bending the straight lines of sight. And you would see the universe reflected there, too. The light from every star in the galaxy that hits the black hole doesn't just disappear, it wraps around it. The entire sky is compressed into a thin, bright ring of light surrounding the shadow. If you looked towards the black hole, you wouldn't see total darkness. You would see the shadow of the event horizon, a circle of absolute nothingness, framed by this thin, glowing halo of trapped starlight. It is the eye of the void staring back at you. This photon sphere is razor-thin and incredibly unstable. It is a knife edge of physics. If you were to drift even a millimeter inward, you would spiral down into the dark. A millimeter outward, and you would fly off into space. It is a place where light hesitates before choosing its fate. For a long time, we thought this view was reserved for science fiction. We thought the objects were too small and too distant to ever be resolved by human eyes. Sagittarius A, the monster in our own galaxy, takes up the same amount of sky as a donut placed on the surface of the moon. To see it, we would need a telescope the size of the Earth. So, we built one. In a triumph of human cooperation, scientists created the Event Horizon Telescope. They didn't build a single giant dish. That was impossible. Instead, they connected radio telescopes across the entire planet, from the volcanoes of Hawaii to the mountains of Spain, from the deserts of Chile to the ice fields of Antarctica. They synchronized them using atomic clocks, timing them to the nanosecond. As the Earth turned, these telescopes scanned the sky together, acting as shards of a single giant mirror. They turned the planet itself into an eye. In April 2019, they showed the world what they found. They pointed this planetary eye at the galaxy M87, 55 million light-years away. And there, in the center of the image, was a blurry orange ring. It was the glowing gas of the accretion disk circling the drain, and in the middle was the dark silhouette of the black hole. We had taken a portrait of the invisible. We had proven that the monsters were real. But as we stare at that image, and as we ponder the physics of the photon sphere, a deeper, more troubling problem arises. It is a problem that keeps physicists awake at night. It is a conflict between the two great pillars of science, quantum mechanics and general relativity. It is called the information paradox. The universe runs on rules. One of the most fundamental rules of quantum mechanics is that information is never lost. What do we mean by information? We don't mean a book or a hard drive. We mean the quantum state of particles, the spin, the charge, the position. If you burn a book, the information is not strictly destroyed. If you could capture every photon of light, every particle of ash, and every molecule of smoke, you could, in theory, reconstruct the book. The universe keeps a ledger. The past is always retrievable from the present, if you have enough computing power. But black holes seem to break this rule. Imagine you throw a book into a black hole. It crosses the event horizon. It is gone. Then, as we will explore later, the black hole evaporates over trillions of years through Hawking radiation. It shrinks and eventually disappears in a final pop. Here is the problem. The Hawking radiation that comes out is random. It contains no record of what fell in. It is featureless heat. So, when the black hole dies, where is the book? Where is the information about the atoms that made it? If the black hole disappears completely and the radiation is random, then the information is erased from the universe. The ledger is destroyed. The past is deleted. This is a catastrophe for physics. If information can be lost, then our ability to understand the past or predict the future breaks down. History itself becomes unstable. For 40 years, Stephen Hawking and other giants of physics argued over this. Some said the information was destroyed. Others said it was hidden in a baby universe. But slowly, a new and stranger idea emerged. A solution that changes our perception of reality itself. It is called the holographic principle. Imagine a soda can. The can is a 3D object holding a volume of liquid, but you can describe everything inside the can, the bubbles, the sugar, the fluid, by writing it on the label. The surface area of the can is enough to describe the volume inside. Physicists began to wonder, what if a black hole works the same way? What if, when the book falls in, its information isn't lost in the center? What if the information gets plastered onto the event horizon? Imagine the event horizon not as a hole, but as a shell, a membrane. When an object hits it, its three-dimensional reality is scrambled and stored as two-dimensional data on the surface. Like a sticker on a ball. The book falls in, but its code stays on the surface. Then, when the black hole emits radiation, it picks up that code. The radiation leaves the black hole carrying the imprint of the data back into the universe. The book is burned, yes, but the smoke contains the text. Information is saved. This solution saved quantum mechanics, but it came with a dizzying implication. If a black hole, the most extreme object in the universe, can be described entirely by the information on its 2D surface, then maybe the entire universe works this way. Look around you, the room you are in, the walls, the distance to the stars. It all feels solid. It feels like 3D space. We move through depth, but the holographic principle suggests that this might be an illusion. It suggests that the entire three-dimensional universe, including us, might be a projection of two-dimensional information stored on a distant boundary. Just as a hologram is a flat piece of plastic that looks like a 3D apple when you shine a light on it, our reality might be a projection of data stored on the edge of the cosmos. We might be living inside a hologram. Gravity, space, and time might not be fundamental. They might be emergent, appearing only because of the interactions of this 2D data, just as heat emerges from the motion of atoms. It is a thought that makes the solid ground feel less steady. It implies that black holes are not just monsters. They are the Rosetta Stones of reality. They are the glitch in the matrix that reveals how the code is written. By studying the edge of the dark, we are learning the structure of the light. But let us step back from the edge of philosophy and return to the physical galaxy. Because black holes are not just storing data, they are actively shaping the cosmos. They are the architects of the night sky. We used to think of black holes as purely destructive, vacuum cleaners that sucked up everything nearby. But we now know they are messy eaters. They are creators. When a supermassive black hole feeds, as we saw, it launches jets of plasma. These jets travel for millions of light years. They carry vast amounts of energy out of the center and dump it into the surrounding galaxy. This energy heats up the clouds of gas in the galaxy. Why does this matter? Because stars can only form in cold gas. Hot gas moves too fast to collapse under gravity. So, by heating the gas, the black hole stops new stars from forming. It acts as a regulator, a thermostat. If the black hole sleeps, the gas cools and millions of stars are born, a starburst. But if too many stars form, some gas falls into the black hole. The monster wakes up. It blasts the galaxy with energy. The gas heats up. Star formation stops. This creates a Goldilocks zone for galaxies. Without the black hole, a galaxy might burn through all its fuel in a glorious, short-lived fireworks display, turning into a dead graveyard of cinders billions of years ago. But the black hole paces the consumption. It ensures that the galaxy burns its fuel slowly over billions of years. It preserves the gas. It extends the life of the galaxy. This means that our sun and the Earth and the atoms in your body might owe their existence to Sagittarius Ace. Without the feedback of the black hole, the Milky Way might have burned out long before our solar system could be born. We exist because the monster in the middle regulates the flow of creation. We are the children of the dark as much as the light. There is one final paradox to explore before we reach the end of time, a barrier that has recently appeared in the equations of physics, the firewall. If the holographic principle is true and information is stored on the horizon, some physicists argue that the horizon cannot be a smooth place. Relativity says that if you fall into a black hole, you shouldn't notice crossing the horizon. It's just empty space. This is the equivalence principle. But quantum mechanics says that if the information is stored there, the horizon must be a seething, energetic surface, a wall of fire. If you tried to cross it, you wouldn't float through peacefully. You would be incinerated instantly by a sheet of high-energy particles. This is the firewall paradox. we have two of our best theories giving us two different answers. One says the door is open, the other says the door is on fire. We do not know the answer yet. It is the bleeding edge of human knowledge. It tells us that we are missing something huge, a piece of the puzzle that will unify gravity and the quantum world. Perhaps space and time are not what we think they are. Perhaps they are stitched together by entanglement, the spooky connection between particles. Some physicists now propose that wormholes and entanglement are the same thing. That connection is geometry. The black hole forces us to confront these questions. It is the ultimate laboratory. As we drift away from the photon sphere, leaving the Hall of Mirrors behind, we look back at the black hole one last time. It sits there, silent, hoarding its secrets. It holds the history of the galaxy on its skin. It holds the potential of baby universes in its heart. It seems eternal, indestructible, a permanent scar on the face of the universe. But as we learned, nothing is truly forever, not even this. In the next and final chapter, we will travel forward in time, way forward, past the death of the sun, past the fading of the galaxies. We will enter the black hole era, a time when the universe is dark and black holes are the only things left, and we will witness their slow, agonizing death. We will see the Hawking radiation steal their mass, drop by drop until the giants are no more. We will witness the final pop of the last black hole, the true end of the universe's story. For now, rest in the mystery. We are living in a holographic projection, breathing processed stardust, orbiting a supermassive ghost, and it is beautiful. We have traveled from the birth of the first stars to the edge of the event horizon. We have peered into the paradoxes of information and the holographic nature of reality. But now, we must take the longest journey of all. We must unmoor ourselves from the present. We must travel forward, following the arrow of time until it runs out of path. The story of black holes does not end with their formation, nor does it end with their growth. To understand their final destiny, we must watch the universe grow old. We must witness the twilight of creation. Let us accelerate time. Let the clock spin faster. Millions of years pass in seconds. The first thing we notice is the changing of the sky. In about 4 billion years, our own galaxy, the Milky Way, will meet its neighbor. The Andromeda galaxy is currently rushing toward us at 110 kilometers per second. It is a collision that has been destined since gravity first reached out across the void. When they meet, it will not be a crash, but a merger, a cosmic dance. The stars are so far apart that they will simply pass through one another like two swarms of bees mixing. But the gas clouds will collide, igniting a furious burst of new star formation. The night sky from Earth will be ablaze with the light of 1 trillion new suns. The two supermassive black holes, Sagittarius A and the giant in Andromeda's heart, will find each other. They will spiral inward, sinking toward the center of the new combined galaxy. They will merge, shaking the fabric of space-time with gravitational waves so powerful they will ripple to the edge of the cosmos. But even this spectacle is just a brief firework in the long night. Let us move further. Billions of years turn into trillions. The era of starlight is ending. The massive blue giants died long ago. The yellow suns, like ours, have swollen into red giants and then faded into white dwarfs. All that remains are the red dwarfs, tiny, frugal stars that burn their fuel so slowly they can live for trillions of years. They are the embers of the galactic fire, but eventually, even they run out of fuel. One by one, the lights go out. The universe grows dimmer. The galaxies, once swirling pinwheels of light, turn into graveyards. They are filled with the corpses of stars, white dwarfs, neutron stars, and black holes. This is the degenerate era. The universe is cold, dark, and expanding ever faster. The galaxies have drifted so far apart that they are no longer visible to one another. Each is a lonely island in an expanding sea of dark energy. In this darkness, the black holes are the kings. They have swept up the debris. They have consumed the gas. They drift through the silent cities of dead stars, occasionally swallowing a wayward neutron star, flaring up briefly in the dark before returning to slumber. Gravity continues its work. The dead stars orbit the galactic center, but over aeons they either get kicked out into the void or fall into the supermassive black hole. The galaxy evaporates or is eaten. Finally, we reach the black hole era. It is a time unimaginably far in the future, perhaps 10 to the power of 40 years from now, a 1 followed by 40 zeros. There are no stars left, no planets, no life as we know it. There is only gravity and the void. The universe is populated solely by black holes. Monsters the size of solar systems drift through the absolute zero of space. They seem eternal. They seem like permanent scars on the face of reality, destined to exist forever. But they are not. Nothing is eternal. Even monsters must die, and the agent of their death is quantum mechanics. In the 1970s, the physicist Stephen Hawking realized something profound. According to quantum theory, empty space is not truly empty. It is seething with energy. Everywhere in the universe, pairs of virtual particles are constantly popping into existence. A particle and an antiparticle appear from nothing, borrow a tiny amount of energy from the vacuum, snap together, and annihilate each other, returning the energy. It happens in femtoseconds. It is the quantum foam. Usually, this happens so fast it has no effect. But at the edge of a black hole, at the event horizon, something different happens. Imagine a pair of particles pops into existence right on the line. One is just inside the horizon, the other is just outside. Gravity is strong here. It grabs the inner particle and pulls it down into the dark. The partners are separated. They cannot meet and annihilate. The inner particle is lost. The outer particle, however, is stranded. It has no partner. It becomes raw. It turns and it escapes into the universe as radiation. To a distant observer, it looks like the black hole has just emitted a particle. It looks like the black hole is glowing. This is Hawking radiation. But nature balances its books. The energy to create that escaping particle had to come from somewhere. It came from the gravitational field of the black hole itself. When the negative energy partner falls in, it effectively subtracts mass from the black hole. For every photon that glows outward, the black hole loses a tiny fraction of its weight. The black hole is evaporating. It is bleeding energy into the cold universe. This process is agonizingly slow. For a black hole the mass of our sun, the temperature of this glow is 1/10,000,000th of a degree above absolute zero. It is colder than space itself. Because it is colder than the background radiation of the universe, it actually absorbs more energy than it emits. It is still growing, but the universe is expanding and cooling. Eventually, the background temperature will drop below the temperature of the black hole. And then, the evaporation begins in earnest. It takes a Google years, 10 to the power of 100, for a supermassive black hole to evaporate. This is a timescale so vast that if you counted every atom in the universe, you wouldn't even be close to the number of years. It is deep time. It is a concept that dwarfs the history of stars the way a mountain dwarfs a grain of sand. But the math is relentless. The black holes shrink. As they shrink, a strange thing happens. They get hotter. Smaller black holes have steeper tidal forces, which tear the virtual particles apart more violently. They emit radiation faster. So, as a black hole loses mass, it evaporates quicker. It accelerates toward its end. For billions of aeons, the black hole is a silent, cold ghost, leaking only a few photons a year. But in its final millennium, it becomes a white-hot ember. It begins to shine. In its final seconds, it becomes unstable. It releases all its remaining mass in a blinding burst of gamma rays. It explodes with the force of 1,000,000 nuclear bombs. And then, it is gone. The horizon vanishes. The singularity dissolves. The trap is sprung. There is nothing left but a bath of particles spreading out into the expanding void. One by one, across the dark universe, the black holes will pop. Like lights turning off in a vast city, the last concentrations of energy will disappear. When the last supermassive black hole evaporates, the black hole era will end. The universe will enter the dark era. Matter itself may decay. Protons may break down into light. The universe will become a sea of photons, cooling toward absolute zero, stretched thin by the expansion. This is the heat death. Entropy has reached its maximum. Nothing changes anymore, because there is no energy to cause change. The clock has unwound completely. Time, in any meaningful sense, stops. It sounds like a tragedy, a cold, lonely end to the magnificent story of creation. But perhaps it is not. Some physicists, like Sir Roger Penrose, propose a poetic twist. In a universe containing nothing but light, scale loses its meaning. Without matter to provide a reference, there is no difference between a universe that is infinitely huge and one that is infinitely small. Perhaps, in that final state of pure radiation, the universe forgets how big it is. And in that forgetting, a new Big Bang becomes possible. A new cycle begins. The death of one eon becomes the seed of the next. This is conformal, cyclic cosmology. It suggests that our Big Bang was not the beginning, but merely the bounce from a previous universe that had evaporated into light. And our heat death will be the Big Bang for the next. We do not know if this is true, but there is comfort in the idea of cycles, in the idea that existence is a rhythm, a heartbeat that spans eternity. But let us return to the present, to the stelliferous era, the era of stars. We are living in the golden age of the universe. We are living in the brief, beautiful window where the universe is lit by stars, where planets can be warm, and where life can open its eyes to wonder. We are the lucky ones. We are the witnesses. We are made of the ash of dead stars, organized by the energy of a living star, standing on a rock that is protected by gravity. We are the universe observing itself. When you look up at the night sky, do not feel small. Feel privileged. You are seeing the universe at its most vibrant. You are seeing the light before the long dark. The black holes are out there, waiting. They are the sculptors of galaxies and the keepers of time. They are the engines of destruction and the vaults of memory. They are the most perfect objects in existence. They remind us that everything is transient. Stars die, galaxies merge, even holes in space-time evaporate. But in that transience, there is beauty. A flower is beautiful because it blooms for a moment. The universe is beautiful because it changes. So, as you drift toward sleep tonight, think of the great cycles turning slowly in the dark. Think of the nebula breathing. Think of the star burning. Think of the black hole waiting. And think of the atoms in your body, forged in fire, borrowed from the stars, currently forming the unique pattern that is you. You are part of this story. You are stardust contemplating the void. The gravity that holds you to the Earth is the same gravity that holds the galaxy together. The light you see is the same light that fights the darkness. Rest now. The universe is vast and old and patient. It has carried you this far, and it will carry you through the night. Thank you for listening to Dreaming Through Knowledge. May your dreams be as deep and wondrous as the sky above. Good night.